Good afternoon, everyone. So I'd first like to thank the organizers for inviting me to speak about 2D materials. And I'm going to speak about 2D materials and the future of electronics. I will just forewarn you that I will probably disappoint everyone in the room because the experts will be disappointed at the lack of details and technical aspects, perhaps, that I'm going to gloss over. And those of you that are not experts in what I'm going to talk about might be disappointed that you have no idea what I'm talking about. But I will do my best job to minimize the disappointment in the room. So let me begin by telling you a little bit about the broad strokes of what I think is going on. And that's to say that we have the collision of atoms and geometry in 2D materials. So on one side, we have the notion of atomism from Democritus, who told us essentially that if you keep dividing things into smaller and smaller pieces, at some point you cannot make your structure any smaller. And on the other hand, we have Euclid, who laid some rigorous foundations for our understanding of geometry. And if we think about these two ideas together and we think about 2 dimensions and atoms, then the natural conclusion to draw is that a single layer of atoms should be the smallest 2-dimensional structure that we can think about. Now, what is also interesting in this discussion about graphene and other 2D materials is that from the perspective of electronics, what's very important is the behavior of our electron energy versus momentum. And so I don't have time to go through perhaps all the detail, and you don't want to see maybe all the detail of the mathematics behind this, theoretical understanding of electron transport through materials. But the basic idea is that the way we think about electrons moving through an electronic material is by thinking about the geometry of the dependence of energy upon momentum. And one of the very curious things about graphene that is rather rare is that geometrical shape is a pair of cones, which I've shown in the bottom right. So our energy versus momentum has this funny cone-like structure, and that's at the heart of a lot of the electronic and optical properties of graphene that made physicists and engineers go crazy with excitement. You can feel the craziness, okay. So, of course, carbon is a very interesting material because it's not just graphene that is an unusual geometric arrangement of our atoms. We also have the nanotubes, which are a one-dimensional manifestation of carbon, and the fullerenes, which are somehow zero-dimensional, although, yes, there are all 3 dimensions there, but the way we think about the electronic properties of fullerenes is as if it is a point-like structure. And of course, graphite, which is the oldest known form of carbon. And already we see that there were 2 Nobel Prizes awarded for the study of carbon, and why 2 dimensions and 0 dimensions were picked out and not 1 and 3. That's a question for people to think about maybe. The reason why graphene in part was acknowledged with a Nobel Prize in 2010 was not so much that it was the first observation of graphene that was made by Andrei Geim and Kostya Novoselov, but more that they succeeded in making the first transistor out of graphene, and they were able to see a lot of interesting physical properties that people had never really looked at before. So, as was already mentioned, the technology for manufacturing graphene is interesting in and of itself. And it was in 2004 that Geim and Novoselov and their team came up with the technique of exfoliation. And the general idea is as follows, that you take a lump of graphite, and it should be a very high quality piece of graphite that is free of other impurities if you can find such a source. And you take some tape and you essentially peel away the surface of the graphite material. Now, this was actually a very well-known trick, to take tape and peel away layers of graphite for a very long time. And usually what would happen is that people would throw the tape away and leave the graphite behind, and then study the very clean, pristine graphite surface that was left behind to study what is going on with your electrons on that surface. But the brilliance of Geim and Novoselov was to not pay so much attention to the graphite, but to look closer at the tape, and then to start sticking the tape onto other surfaces, and to look very closely at that debris which was left behind, and to suspend belief for the moment that, well, maybe you could peel away a single atomic layer. Now, if you had applied for funding to do that experiment, I'm sure you would get a rejection letter of fundable but not funded or something of the sort. But they nonetheless pursued this curiosity-driven experiment, and they found that indeed, not only can you exfoliate single layers of carbon atoms, but you can in fact put electrodes on them and study them, study their electronic and optical properties. Now, on the top right, you see an image of graphene pieces that have been deposited onto a surface of oxidized silicon. And you'll notice that you can see them with your eyes. And that's actually one of the very amazing properties of graphene, that even though it is a single layer of atoms, the inherent strength of coupling between electrons in the graphene and the photons that constitute the light that you are using to image the graphene is sufficiently strong that you can see it with your unaided eye. Now, this session is on the subject of advanced manufacturing. So Scotch tape is, although a very difficult, well, I should say, although it's a very interesting piece of manufacturing equipment, there is a need to be a bit more serious. And there was an important advance that was made in 2009 on the synthesis of graphene by the groups of Rolf and Colombo. And this relies on a little bit of organometallic chemistry. And the idea is as follows, that you take a copper surface and you warm the copper surface to a temperature of about 900 Celsius. And of course, you've done a good job to clean that copper surface. And you expose that hot copper surface now to a hydrocarbon source. It can be methanol, ethanol, my favorite, or other hydrocarbon sources. And that hydrocarbon will decompose on the surface of the copper. And the carbon atoms that are resultingly produced, they do not sink into the copper because they are not soluble in the copper, but they are still somehow bound to the surface, and they will self-assemble into a graphene layer on the copper surface. So once you are done with this synthesis process, all you have to do is etch the copper away and capture the graphene. And this is actually easier than it sounds. And you can capture that. So what you see in the bottom right is a 2 centimeter square piece of monolayer graphene sitting on a quartz wafer. Companies now have produced graphene by a similar method on the order of hundreds of meters in length. So this is a manufacturing process that allows us to have great quantities of graphene if we just knew what to do with it. Now, I will mention that I personally find this time to be very interesting because we're really going through a renaissance of discovery in some way. So there's a fantastic book called Electronic Structure and Electronic Transitions in Layered Materials, which gives a review of hundreds of layered compounds. And in the dedication of this in this book, it's stated that it's a tribute to Professor Franco Bassani, to whom the Italian tradition of the field of layered compounds, as well as in other fields of solid-state physics, owes much. So Franco Bassani was, for a time, the director of the Scuola Normale Superiore in Pisa. And already in the early 1980s, it was known that there are hundreds of materials that have a layered structure similar to that of graphite. That is to say that the atoms are arranged in sheets that are very tightly bound into sheets, but they are very weakly bound between them. So it should be possible to peel all these layered compounds apart. And so if we look at the structure of other layered compounds, in fact, we find that it's a very interesting world. We have graphite, of course. We have white graphite, which is boron nitride, where we replace the atoms of carbon with boron and nitrogen. Black phosphorus is a very recent addition to this in terms of experimental work. We have the transition metal dichalcogenides, sesquichalcogenides, monochalcogenides, metal halides. Fantastic semiconductor materials. We have high temperature superconductors. We have materials that don't even fall neatly into a classification, such as magnesium diboride, which is a very interesting superconductor in and of itself. And we have, of course, very complex structures like mica, which people have known about, of course, for thousands of years. And it is one of the things that you are probably familiar with mica is that it is quite easy to peel apart. So when you look at actual pictures of these materials, you see that already there is a wide range of properties that is captured. You see things that are black, things that are white, things that are shiny, things that are very colorful. And this is an indication that there is a very wide range of both electronic and optical properties that are accessible with the layered compounds. And it's only now that we are revisiting what's known about layered compounds in their bulk crystalline form in the realm of peeling them apart to single atomic layers and asking the question, what happens when you take this metal and you peel it away into a single atomic layer? Will it stay a metal, or will it become a semiconductor? Will it become an insulator? And so this then brings up the topic of what do electrons do in 2 dimensions. So in the top row, I show you the energy momentum curve, which corresponds to cones. And that is the energy momentum relationship that is appropriate for electrons sitting in a piece of graphene and also in a funny material called silicene, which is composed of silicon atoms. And I should mention that silicon does not involve, there is no silicon analog to graphite. So you cannot find silicene in nature. One has to force silicon atoms to live on a surface. And if you do force silicon atoms to live on a surface, you can coax them to take the form of silicene, which is a form of silicon that is not found as a layered compound. So it's telling us that even the field of 2D materials is having new members join in. That is not just the exfoliation of existing bulk crystals. Now, silicene and graphene are very good conductors, or what we like to call sometimes semi-metals. And they are appropriate to making very good electrical conductors, but they are not appropriate to making very good transistors. So one of the things that has been driving a lot of research in graphene over the last decade has been the search for a way to make graphene a semiconductor. So people have attached other foreign atoms to try to change the shape of the cones into a set of hyperbolas. And there are, in fact, materials that naturally have hyperbolas that describe the energy momentum relationship of electrons. Two of those material families are phosphorine, which is the single layer of black phosphorus, which looks like a honeycomb arrangement of your atoms, but they are phosphorus atoms, and the phosphorus atoms would prefer to arrange themselves to have these puckers in the structure, so we say it has a puckered honeycomb lattice structure. And there are also the chalcogenides, which is a very large group of 2D materials that are generally known to be semiconductors. And if you make a hyperbola which has a very large separation between the 2 parts, then this is what leads to insulating electronic behavior. And so one of the most well-known examples is boron nitride, which looks very similar to graphene, except you have the alternation of boron and nitrogen atoms that compose the material. Now, for electronics, we actually need conductors, semiconductors, and insulators. And it seems now that we have all 3 of these materials in a 2-dimensional form, which tells us that we should be able to make transistors and any electronic device we can completely out of 2D materials. And so this idea has not escaped attention. It was already André Geim and Kostya Novoslov who proposed the idea of what we call sometimes 2D heterostructures or van der Waals heterostructures, where one, if one is using the Scotch tape method, one buys several rolls of Scotch tape and finds a very dedicated graduate student to spend weeks peeling apart layers of atoms and then cleverly arranging them one on top of the other to make a custom designed structure solely out of 2-dimensional arrangements of atoms. And this tells us that the degree of freedom for designing electronic devices is no longer bound by just thinking about what material are you going to choose, but what material are you going to choose for layer 1, layer 2, layer 3, and so on and so on and so forth. And it also challenges our understanding of electronics in many ways. So a very important device for electronics is the so-called light-emitting diode, which is essentially a combination of 2 different semiconductor materials. And it's the source of light in most of your portable electronic devices, a little flashing blue light or what have you. Now, the way that we think about diodes in electronics is thinking about a bulk semiconductor here and a bulk semiconductor there. And all our theory comes from the theory of bulk semiconductors. But now we are forced to revisit what happens if we take one layer of semiconducting atoms and another layer of semiconducting atoms. And we can no longer think about our material in the usual three-dimensional way. And so there's a lot of revisitation of old semiconductor physics from the 1960s that now has to be appropriately modified to answer the questions of what happens when we combine different semiconductors. So now let me tell you about something that's a bit of a problem. So on the top left, you see a server farm, which is the size of 10 American football fields, where I guess we don't have that many Americans in the audience, so for the rest of us, that is about 53,000 square meters. And this is just filled with computers and electronics. And so from a very interesting report that was funded by the National Mining Association and the Coalition for Clean Coal Electricity, they note that, in fact, something like 10% of world electricity production is being spent on the electronics that is housed in those server farms, which is what is the source of whatever you are watching on YouTube and elsewhere. So there's a huge cost, an energy cost to our use and our dependence upon electronics. And this is one of the biggest challenges for electronics. And if we look at computing and the energy cost of computation, there's been a steady trend to make things more and more efficient. The abacus is moving large rocks around. That is not an energy efficient process. Having a mechanical register like what Pascal proposed in the 1600s, that's an improvement, but it's still not optimal. We had vacuum tubes used in computers that weighed 30 tons and filled a gigantic room in the 40s. Once transistors replaced vacuum tubes, that made our computers smaller, but you would still need a whole room to house it. And it was only in the 70s that finally you had a single computer that is housed on a single silicon chip. Of course, since the 70s, our transistors have just gotten smaller and smaller and smaller. Now, there is a very famous problem about energy consumption in electronics. And that started with James Clerk Maxwell thinking about something which we now call Maxwell's demon, which kept very distinguished thinkers up at night, such as von Neumann, Shannon, Brillouin, Landauer, and Bennett. Now, the energy cost to perform one logical operation is 40 kT. If you don't know what kT is, that doesn't matter, because what is done in practice is we consume something like 1,000,000 kT. So there are orders of magnitude of improvement that we have left ahead of us in terms of how we consume energy to process information on a computer chip. And this is something that Gordon Moore realized back in 1965 when he first wrote about the law which we call Moore's law. And he noted that power is needed primarily to drive the various lines and capacitances. So in the bottom you see a picture of a chip where these transistors are at the bottom and they're really tiny things driving gigantic pieces of metal. And it's for this difference in size between the metallic wires that are being driven and the tiny transistors that we are consuming so much energy. So there is a search to try to produce a transistor that is somehow better, that operates at a lower voltage. That means that your wires can be run at a lower voltage. That would then do something to reduce the amount of energy consumption per logical operation in our electronics. So if you look at what transistors have already been doing, just driven by the progress in industry, on the top you see a picture provided by Intel. And in the top left, I'm showing you a water valve, which is basically what a transistor is. So you have a source of water, a drain for water, and you have a valve which turns the flow of water on and off. And if you notice, the red arrows are pointing to a dimension which is getting thinner and thinner, and that is the active semiconductor region through which electrons are flowing. And that's effectively the size of the valve for our electrons, and they're getting thinner and thinner and thinner, and the logical limit to this progress is the two-dimensional limit where we have a single layer of atoms that is conducting electricity. Now, it's not entirely known what happens to transistors when we reach the 2D limit. There are some things we know, and there are some things we still do not know. So in the bottom, I show a little cartoon image of a two-dimensional material transistor with a gate source and drain. And in the bottom right, you see a optical microscope image of a very giant form of two-dimensional material transistor. But it's something that is driving our research effort to try to understand what is the optimal way to build a transistor when your channel is made out of a two-dimensional material like black phosphorus. Now, I see a red dot, which is telling me to hurry up. So let me just finish on two points. There is still a lot of fundamental understanding to gain. So let me just point out one very interesting quantum mechanical phenomenon related to two-dimensional materials. It so happens that from the geometry of our atomic arrangement in, let's say, graphene, when one takes an electron and forces the electron to make a closed orbit, there is a phase that is picked up by the quantum mechanical wave function of that electron. And that phase is not necessarily zero. And what this corresponds to in a very rough kind of way is if you look at the Mobius strip on the top right, if you start on one part of that Mobius strip and you make one circuit around the strip, you will find that you will actually require two traversals of that strip before you come back to the same point. And that's an interesting phenomenon that we can actually observe in electrons in two-dimensional materials for reasons that are quite deep and very enjoyable for those of us that enjoy those things. But the consequence is that when you look at, for example, the resistance of a two-dimensional material under the application of a magnetic field, you will see that there are funny oscillations, and the phase of those oscillations is controlled entirely by this Berry phase phenomenon. And one open question is, can we use these bizarre phenomena to make an improved transistor? This is something that keeps me and my graduate students up at night. And I should also say that 2D materials offer us other avenues to revisit old ideas. So why not make an electromechanical switch out of a single layer of atoms? So in the bottom left, you see a false color image produced by a scanning electron microscope of a monolayer of graphene, actually two strips of monolayer graphene that are suspended above trenches. And it's very difficult to see the shadow, perhaps. But these are a single layer of carbon atoms that are suspended above a trench. And it turns out that you can apply a voltage below and kind of get the graphene to deflect by some electrostatic attractive force and close the switch, then you can open the switch. And why not try to make the smallest switch possible? And can we make a reliable electromechanical switch, which is somehow going back on the history of computation, but on such a miniature scale that all the scaling of energy consumption is different from that which we know of now. So let me just say then that 2D materials are a new and diverse material family. The interest is in new physical phenomena, in new devices, and new manufacturing techniques. Our progress is really driven by curiosity, I would say, at this point, and there's a huge possibility for transformative change in electronics. Thank you very much for your attention.
Go ahead.
Okay, so the question I've got is, how do you think Geim and Novoselov got the idea of looking at the rubbish rather than the really nice carbon material in the first place? So what made them look at the sellotape?
Who is that question addressed to? Sorry.
Maybe both of you?
Both of you. Both of you.
Both of you. So Cecilia first.
Was also a way of preparing like crystals for different spectroscopy or microscopy measurements. Well, I guess I had the intuition that something more interesting was on that side of the tape. If you have something to add.
Yeah, from my understanding, one of the motivations for that whole line of work was to try to make a transistor out of metal, which is something that we're told never to do. and it was a graphite that attracted the attention of that team, and I believe it is recorded somewhere in Geim's Review of Modern Physics article about who it was in the laboratory that came up with the idea of actually looking at the Scotch tape, and it was not directly, I think, Andre and Kostya alone. There was a third person, but I don't recall who it was. They're probably the best people to ask this question.
Yes, go ahead.
My question was really just how far would this box go? My question was motivated by Thomas's talk, but it's probably applicable to you all. I'm not in this field at all, so it might be a stupid question. Thomas, you talked about layering layers of graphene and materials. So my question is, when does a 2D material become a 3D material if you're layering something?
That is a fantastic question. And that's actually a question that reviewers of articles sometimes ask. So there's several notions of two-dimensionality here. One is the two-dimensionality from the perspective of being able to cleave a crystal apart into an atomic layer. And so that is asking about what is the anisotropy and the strength of the bonding between atoms in plane and out of plane. And so that can be quantified. It's difficult to make those quantitative measurements, but they can be quantified. And so that tells us something about the two-dimensionality from the perspective of chemical bonding. But in terms of electronic properties, it is possible to coax electrons to behave as if they are two-dimensional in a bulk semiconductor. So in all your cellular telephones, you are using technology that in fact relies on this very fact. So the transistors that are amplifying the signal that is picked up by your cell phone antenna, that first amplifier with that first transistor must be very low noise. And it turns out that forcing your electrons to behave as two-dimensional electrons in a three-dimensional bulk semiconductor is the key to make that happen. And the way to think about it perhaps is that what's needed is you need to confine your electrons in a quantum mechanical state that suppresses any motion in, let's say, the vertical direction. And so this is akin to taking a guitar string and forcing the guitar string to only play one note because it's so taut that you can't excite any other note than the lowest note. So that just means that you have to squeeze the electrons into a small space, but it doesn't have to be a single layer of atoms. You can still have a finite thickness of material and force your electrons to sit as if they are two-dimensional.
Just going to put the laptop down. Hang on.
Thank you. My question was probably aimed towards Thomas as well, actually, although maybe either of you would want to jump in on this. We've kind of become accustomed in our electronics that they're not easy to peel apart in terms of in computer chips and things like this. Obviously, assembling these really interesting stacks of materials, we do it at room temperature and this kind of stuff. If they're easy to put together, are they easy to fall apart? And is that an issue in electronics?
You mean, can we shake our 2D layers off each other?
Yeah,
That sounds
we
like
often run chips at high temperature, for instance, so could they just fall apart?
Oh, things always fall apart. If you ask the graduate students in the lab, there are very many different mechanisms for failure that we still have to understand. So even how you put the metal contact onto a two-dimensional material, it's not trivial for a very interesting reason, which in retrospect is quite obvious. And it goes something as following, that if you have a two-dimensional material then the bonding is very strong in plane, and you have very weak out-of-plane bonding. So that means when you want to put a third material on top, like a metal electrode, to have efficient injection of an electrical current, you have to find a way to attach something to this 2D material that doesn't really want to bond strongly to anything atop it. And that means that there are better ways for the fabrication to go than other ways. In practice, though, it's the behavior of materials on that scale. The forces are so enormous that in practice it's not really a problem unless you are thinking about macroscopic objects. So it's something that we don't really see that particular problem yet, but who knows? Who knows? I mean, it has important practical implications for the perspective. If you want to make a switch, for example, that operates on the basis of making an electrical contact on the basis of mechanical contact, the sticking forces between the two surfaces and how many times you can actuate that contact and breaking of contact is something that's not yet well understood, but it will most certainly need to be, because if you think about the number of times your transistor will switch in a chip, it's billions upon billions of times, so you really need to make sure you understand that. So it's definitely an open question, I would say.
Actually, I have another question, for Cecilia. Actually, it was obviously this layered structures were really interesting, and you showed these really cool 3D systems. Is there any feasibility of combining these two, of making three-dimensional structures of layered materials?
Yes, well, one of the ideas is also to combine this two-dimensional material with graphene, making three-dimensional construct. And that would expand the function that this three-dimensional construct can have, also considering the catalytic properties of these 2D materials and their strong light-matter interactions, which are limited in graphene. Yeah.
Actually, I have a question as well, if you don't mind. You mentioned quickly in your talk that you talked about 0D, 1D, 2D, 3D. I mean, people have done quantum dots for a long time, 0D materials. 3D materials, of course, have been known for a long time. 1D materials with nanowires, there's been a lot of work. You didn't get too much into what's so special, in your opinion, about 2D compared, for example, to 1D, 0D. You mentioned that 2D devices, but in the end, you could also have 1D devices if you could stretch a graphene ribbon into, thin enough that basically becomes a wire, a graphene wire. Or a carbon nanotube basically is a 1D material. So what's so special about 2D? Is it because it's easier for manufacturing integration, or what do you see so special about that? Maybe Thomas first and Cecilia after.
Right. So there are many aspects to this question. So first of all, I should say that there has also been a lot of work on two-dimensional systems, in the sense, not that the atoms have a two-dimensional nature to them, but that as I mentioned, there are ways to coax electrons to sit in a two-dimensional state in a bulk structure. So this is like the physics of quantum wells that have been studied for a very long time and have brought about a lot of very interesting new physics to us, especially under the application of a magnetic field, where you can, in very clean systems, study what happens when the dominant physics is driven by the way electrons interact with each other. From the perspective of electronics, there's a few other things. So obviously a planar technology is very beneficial. It was some time after the first transistors were made that electronics really took off, and one of those enabling discoveries was that you need to be able to make things in a planar fashion from the manufacturing perspective, because the entire semiconductor industry is based essentially on planar technology. So that's one aspect. Another one that I didn't really mention is about what is the optimum transistor. And you really want to have a very short transistor and also very wide. And the way to think about it is like from a perspective of a valve. You don't want your valve to be very long, but you do want it to be very wide so that it can carry a lot of current, whether it's an electrical or water current. You want a large current carrying capacity, but you also want it to be very short so that there isn't too much loss of pressure or loss of voltage, however you want to think about water or electricity. So all of that is favorable for two-dimensional materials. The 1D structure is very interesting, but it's not necessarily optimal for transistors. There's one other important distinction to note, and that's that in 1D, you don't have the freedom to wrap one particle around another. But in 2 dimensions, you do have that dimensional freedom. So it says that 2D is inherently different than 1D. And I'm not going to say that 2D is better than 1D, but it's just you have a different set of dynamics that is present that means that you can see different physics. And that's what some of us choose to be 2-dimensional people, and some of us choose to be 1-dimensional.
Yeah, so you've both clearly stated that this is an awesome material and that this is going to revolutionize our world. And then I wonder, even though you said, Cecilia, that this might be good also in environmental applications where it can soak up oil and these kind of things, is there any more in general, any ideas about what this material that is so strong, that lasts forever, what it does is in our environment? And if we are going to bulk produce it, is it going to be a problem or not?
Well, there are several studies on also in terms of toxicity, etc., considered for nanomaterials. So it all depends also in how they are embedded and what they are embedded, those materials. So, and at the moment, like graphene can really enable several different new applications of composites based on polymers. So, and the strong emphasis is also making those materials long-lasting. So while polymers at some point degrades, and then you have somehow to get rid of those polymers, graphene-based material potentially they can last much longer. So they can be used for long last of time. So we would consider in that way graphene-based material like material that we never really get rid of. So that could be a possible advantage. But obviously the field is still at the early stages, so it's difficult to really envision the first real application and for how long those materials can actually sustain. Yeah.
Quick question, are these transparent? I'm kind of curious if I'm going to see all sorts of see-through computing down the line because of this.
That's very interesting. The transparency of the single layer of atoms depends, of course, on which atoms you choose. But let's take graphene as an example. One of the very curious properties of a single layer of graphene is that it is, let's say, 97.7% transparent. And that number is basically 100% minus 2.3%. I think I can do the math right, I hope. And that 2.3% is a very important number. It's pi times something we call the fine structure constant, which is a kind of important physical constant that denotes the strength of electrons, electron coupling to photons. And it is indeed the case that a lot of the interest in graphene and producing large sheets of graphene is driven by the interest to produce flexible and transparent touchscreens. So a large number of handset producers are looking at graphene as a replacement for the existing conductive electrodes such as indium tin oxide. But this remains a very large challenge to displace indium tin oxide because it is so cheap. And so economics is now a very big factor in determining whether graphene will ever replace existing transparent conductive electrodes. But that's something that has not escaped the attention of a lot of people that drives interest. And there's other, applications perhaps in photovoltaics and so forth, but it's an active area of research.
Yeah, I would say that those one of the main interests actually is also in this material is the fact that they are transparent. So also, if you think of assembly up to 10 layers or more of this material, still, this assembly will be transparent, so you can see it through. So, and devices, to make effective devices of these materials, possibly up to 30, 40 layers will be enough, and they would be still transparent. So it's one of also the main plus of these materials. Yeah.
Pass it down the line? Pass it down the line. Okay. I think you touched on this a little bit with, you mentioned about nanoparticles, right? Are there health issues with the graphene materials? Per se, just so with the nanoparticles, the concern is people can make these and then they get in the atmosphere and then they're inhaled, right, and stuck in your lungs. Are there similar health issues with the 2D materials?
Well, 2D materials can be actually much larger in terms of one dimension, can be up to millimeters or meters even. So in that case would be just adhering a specific substrate. Obviously, if we reduce both sides of these 2D materials, we make those close to 1D material, then there will be, there are studies actually on possible toxicity related mainly to the dimensionality as any other low dimensional material. So yeah, would be, if there is any concern, it's mainly for those graphene or 2D materials which are manufactured very small. So they are comparable to other nanomaterials, and the main issue is the dimension, not much the chemistry that they contain, but it's their dimensions also.
Okay. And just to do with the cost, have people done life cycle analysis to look at the cost? Because obviously you need very pure materials, correct? And so the cost to make those is quite high, but if they last a long time, then that offsets that cost. Have people looked at the economics of that?
Yes, people are strongly looking into the economics, especially for the liquid phase produced materials. So how we can decrease the cost to make it actually effective. So this is also one of the reasons that can dictate some applications versus other applications. So the cost involved in making those materials, like using high temperature in a furnace, like the chemical vapor deposition methods involve much higher cost than making those materials in liquid phase, for instance. So those are all pros and cons that have to be taken into account then to decide what are the advantages of using those materials for novel application related to the cost of making those. Yeah.
Very nice talks. Let me ask you a provocative question here. So when would you think graphene will go out of fashion? Why?
Well, sometimes I guess also the other 2D materials now can be considered somehow more fascinating than graphene itself. So, well, it's not out of fashion, of course, but there are also these other two materials that sometimes attracts more attention than graphene itself now. I don't know if you want to add something.
Yeah, I'm weighing my words carefully. There have been some people who have said graphene is dead, but I think there's just the way that graphene itself started was very much out of the mainstream in some way, and so I think there may be a reduction in emphasis on graphene itself, but I would be hard-pressed to believe that there are still not more surprises that lie ahead. It's very difficult to predict the future with any accuracy, so who knows? I mean, now I would say that there's much more interest in all variety of 2D materials, and to give you an example of perhaps of how graphene still plays a very important role in electronics, the way that electrons move in one layer is affected by what is the environment around it. Because your electrons are essentially on a surface, they're incredibly sensitive to everything going on around them. And so graphene is great because it's kind of like a two-dimensional metal. And so maybe in some cases, and it's already seen in experiments, that if you put a metal layer next to your semiconductor layer, the electrons in that semiconducting layer are somehow protected from the environment by the graphene, and you get improved electronic behavior. So there's still results like this coming out where graphene still has some very nice uses and surprises for us, and I think it's just limited by our creativity. That's what I would say. But there's certainly some people that will say it's out of fashion, but that's fine.
If I made just a comment, in the microelectronics industry, people have been saying that silicon is dead since the mid-70s, roughly.
Yeah.
That's another question for Thomas. You mentioned indium tin oxide and its widespread availability. In terms of sustainability, is there enough indium in the world to bypass the potential usefulness of carbon-based electronics? Any comment on?
Yeah, definitely, that's something that's actively debated, and presently, although indium prices have gone noticeably higher, it's manufacturing cost that also drives a lot of this. That is to say, it's not just the materials, but all the infrastructure that goes around the process. And presently, the price points for indium tin oxide is much more appealing than graphene. But that's not necessarily to say that it will always be that way, but at the present time, that is the situation.
Thank you. Oh, I think I just delivered it to you.
Thanks. Yeah, I wanted to ask about the electronics and the efficiency. You gave the discrepancy between the Landauer limit and today's electronics. So what is your opinion realistically with, let's say, those advanced electronics? How much closer can we get to these Landauer limits? Because also you seem to indicate that one of the problems is actually the wiring between the transistors, and that would have probably stayed the same, right? That challenge. So yeah, I'd be interested in your comment.
Sure. So this problem is known for a long time, and there are a number of solutions that are floated out there, and this is a very active area of research now to try to figure out what can be done to improve energy efficiency to get closer to this thermodynamic limit, because we're so far away. There's so much room, and it's not an easy problem. So there have been some proposals to use light instead of wiring. So you imagine like a little miniature waveguide for light to connect electronics on one side of the chip to another side. And that brings in a lot of complexity about the efficiency of the light generation, the light transport, and then the transduction of light back into electricity. And it's something that drives a lot of nanophotonics research, for example. In terms of staying in the electronic domain, the idea is the following, that if you could somehow reduce the voltage at which your transistor operates, then you would be able to reduce the voltage that you are charging up the wires and discharging. And the amount of energy that's consumed goes as voltage squared. So right now we're operating at 1 volt, and that 1 volt is determined by the transistor. Now, if you could design a transistor that operated at half the voltage, you would then be consuming about 25% of the power that you were before. The challenge is that you want to make a transistor that operates with lower voltage, but the amount of current change that you can get out of a transistor per unit voltage is definitely limited by the physics of the transistor that you are using. And so there's also a thermodynamic limit there, and essentially we're very close to that limit for the way that transistors are currently designed. And the way that they're currently designed is that you have a potential barrier, and you put the barrier up to block electrons, and then you put the barrier down, and electrons can go through. Proposals to change this into another technology would be, for example, that you put a barrier up, and that barrier is always up. And it's just that you make the barrier either very thin or very long, and you rely on the quantum mechanical tunneling of electrons through that barrier. And it turns out then that you can, in principle, have much more current change per unit voltage change, and so that would allow you to reduce the amount of voltage that you use. But there are a lot of problems to overcome still with those kinds of ideas, but it's very much an active area of research.
And that will be done with those 2D materials, is that the
Yeah,
idea?
there are already studies on trying to use these two-dimensional materials to control the tunneling, the quantum mechanical tunneling. And the advantage of the 2D material here is that they are so thin that it's very easy to control the profile of that potential barrier, more so than with a thicker lump of material.
I was just wondering, so you've already sort of started to get to this a couple of times, but what level of convergence is there between the quantum computing world and the 2D electronics world, if any?
There's definitely some interest, but I would say right now there's a tangential relationship between the two, in the sense that it's not quantum information that's driving progress in 2D materials, and neither is progress in 2D materials driving quantum information, although there is work to etch out little patterns in your graphene, for example, to capture one electron and to manipulate the spin of that electron to create a qubit for quantum information. But there's still very many material challenges there, and it's not, I would say, the mainstream. The mainstream is not to have an intersection between the two. It's tangential, I would say. Oh.
Thank you. Excellent talks. I have just a question on when you do fabrication of these 2D materials, do you get into the green chemistry principles, or do you go through the conventional chemistry and physics? It's both for both of you to answer.
Well, obviously we do try the green chemistry route first, and and then use conventional chemicals whenever it's needed. But eventually we try to make all the processing. Once we learn how to make the processing with conventional chemicals, then we can also see for more green chemistry routes. For instance, there is quite an emphasis now on ionic liquids, using ionic liquids for exfoliation of these 2D material rather than organic solvents. And so obviously it's a path that is pursued by scientists. Yeah.
Okay, thank you. And the next question I have is, beyond electronics, do these 2D materials have applications in the health sector? Or they might have potential applications?
In the health set. Yeah, well, there is quite an interest in using those materials for instance, drug delivery or bioimaging or various differentiated areas of interest in biology or even in bioelectronics. So to make devices to be embedded or to be just as a tattoo, which can be attached to our skin for monitoring body function. So there is a wide range of possible application of these 2D materials for devices related to biomonitoring of functions. Yeah.
Okay, thank you. So.
Maybe one question, Cecilia. You showed those sponges for oil. What advantage there? It was not clear to me what advantage graphene has over other spongy materials there? I mean, how does it behave differently?
So graphene is mechanically very strong, much stronger than any other polymers, but at the same time it's flexible. So ceramics material are not flexible as graphene. So graphene presents the advantages of ceramics as well as polymers. In addition to this, it's also conductive. So we can make sponges which are mechanically much stronger than polymer-based sponges. We can also sponges made based on ceramics materials, so what are called highly porous materials, but it will be very rigid. So they will not have the flexibility or the elastic plastic properties of graphene-based sponges. And in addition to that, either ceramics-based sponges or polymers-based sponges are not generally conductive. So those sponges made up of graphene can really have three different properties, which encompasses the property of ceramics, polymers, with the addition of electrical conductivity. So.
And what about the matrices loaded with carbon nanotubes, for example? That could be another way to do something like that, or is it?
Yeah, there have been research previously also in trying to make those three-dimensional structuring with carbon nanotubes. Graphene, in that sense, is also, we have to consider the cost of making those materials, and graphene with these two-dimensional layers, which can be as large as micrometers, they can induce they can make much stronger structures, much more solid than, for instance, carbon nanotube-based three-dimensional structuring. So there is an advantage of having this two-dimensional geometry, which enables stronger van der Waals forces to be recreated, stacking together just a few graphene layers. If you stack together too many graphene layers, we go back to graphite, and we have a very rigid and a brittle material at the same time. But having just a few layers of graphene enables having stronger van der Waals forces to give the structure together, but at the same time maintaining the flexibility.
Actually, I have another question. I was wondering, we talked a little bit, Thomas, before the talk, so you know the punch, but one question I'm really wondering is, for you in the community, how did the 2010 Nobel Prize change the field, change the community, change the momentum in the research? What kind of change did you see in your community after 2010?
Sure. So one very noticeable phase transition, I would say, was that, and speaking very frankly, was the curiosity-driven nature of the research was somewhat overtaken by the influx of funding through a lot of graphene centers and so forth, with an emphasis on technology deliverables. So the expectation was raised that, oh, in 5 years we need to have graphene transistors replace silicon. And these kinds of things, I think, are quite destructive in the sense that they do sometimes give a false sense of the timeline required to really work out all the details to produce something that really works. On the other hand, there was also much more visibility for the work, which there's these two aspects. So it was great to see the excitement, and you could have undergraduate students who know about graphene because it's all over the press. But at the same time, funding administrators sometimes then believe that, oh, when will I be able to have my graphene computer? I don't know. So those were the two things that struck me the most, I would say.
Cecilia, what about you?
Well, I guess actually it was obviously in terms of, as Thomas was mentioning, as this event has been heavily covered by the press, increased very much the awareness, consciousness about discovery of new materials for new technologies. So I can see also more and more undergraduate students who knows already what is graphene, what are the properties of graphene under two-dimensional material. So I think has very much spread much more consciousness of material science also from material science point of view. So I think definitely the impact has been enormous, and all of us are benefiting out of that.
Okay.
I have a question for Cecilia. I was really impressed by this picture of the syringe squeezing out a line of graphene onto the surface. Can you say something about what would be required to get a 3D printed graphene structure? And if so, what kind of properties would this have that you wouldn't be able to get with other materials?
Yeah, indeed. Actually, recently 3D structuring of graphene has been demonstrated with a 3D printer. And so the key point is how we assemble together these sheets in the suspension. So what is the concentration, how we control the chemistry of this suspension. And often we need also to add a few other molecules which helps linking one layer to the other one a little bit more strongly, but not too strongly. And yes, again, the mechanical properties are really different. So depending on how these flakes are assembled, they can be very strong and rigid, or can be very elastic or plastic. So, and depending on those properties, they can be used for different applications. So we can think of making batteries, electrodes, or capacitors, electrode based on graphene, because we can carefully control the shape of those electrodes up to the micron level, as well as we can make more large devices for bioelectronics applications. So then the range of application can be very much diversified once we can identify reproducible ways and a systematic way of dictate these different mechanical properties in the 3D structuring.
Thank you.
I guess I'm curious about the hydrogel morphologies that you're showing. And I'm curious whether or not magnetic fields can affect the hydrogel morphology internally.
Yes, well, possibly if we can also incorporate magnetic particles, or so we can also control the, let's say, the structuring with an external magnetic field. We need to induce some, so by assembling these 2D materials, or graphene in particular, with nanomaterials which have magnetic properties, then we can possibly control with an external magnetic field. Is that on the line of, I guess, what you were asking? Or
Yeah, I guess I just didn't know if the material itself was influenceable by magnetic fields or not, and whether or not you could use that as a dominant factor in trying to arrange the internal morphology of the material as it sort of forms into a hydrogel like you were showing.
Making like adding to graphene other materials, then we can actually perhaps have some we can try to control possibly this three-dimensional structuring with an external magnetic field. Otherwise, the structure per se is not really controllable by a magnetic field. Yeah.
Thanks.